Hello friends, today we will see impact of non-symmetry in differential amplifier. So impact of unsymmetry, on common mode gain of differential amplifier. So we want ACM equals to 0 so that common mode rejection ratio ADM upon ACM equals to infinity. So this we want ideally. This is ideal case. Now because of non-idealities or unsymmetry in differential amplifier, this ACM is not equals to 0, and if ACM is 0, common mode rejection ratio is infinity. It means whatever noise coming on which is common to both input fully rejects and it will not pass to output. Okay, now we consider two cases. So case 1, case 2. So how this unsymmetry can come? So consider this differential amplifier. So this is RD. This resistance, both resistance, there is a possibility can be different, say del RD. This much difference is there. So this is M1, M2, and suppose both M1, M2 are same, and GM is transconductance for these two, and here we are giving VICM, input common mode, and this is say our tail resistance. In second case, suppose resistances are same, both are same, but these two devices differential pair, are different, say maybe different W by L, suppose, and this is having transconductance GM1, this is having transconductance GM2. Okay, but these are same. So this is say VO1, this is say VO2, this is VO1, this is VO2, this is VDD, this is VDD, and this is VICM. Okay, so consider these two cases for both, and this is say VT, this is say VT, and for both cases we will find ACM. We will see how symmetry in load resistance and unsymmetry in input pair, these two unsymmetry, how these are going to impact common mode gain, which will impact common mode rejection ratio. Okay, let's see. Let's start with our case 1. So in this case, if we consider this lower portion, this is totally symmetric, and this will act like a source flower. Any signal coming here, says VICM is say small, say this is delta, So it is going to change this tail node in similar fashion. So we consider it like this is say RT, and say this is VICM, this is VT, this is VT, and now because of these two, we can consider it like 2W by L. Say this is W by L, this is also W by L. So we can make it like this. This is the equivalent circuit for lower portion. So what we are going to do, we are going to see how much Vt is going to vary. So I tail whatever Vt is varying divide by Rt. Now both devices are symmetric, M1 M2. So ID1 equals to ID2 equals to I tail divided by 2, and VO1, so we can write at Ohm's law equation at output, VO1 by RD equals to IT by 2, and 0 minus VO2 by RD plus delta RD equals to IT by 2. So from here we will find Vt function of VICM, and we will put in these two equation. Then we will find VO2 minus VO1 by VICM, which is ACM. Okay, so let's find out. So this is source follower, and from here if we see resistance, so from here to here it will be 1 by GM of this device. So this device GM will be not only GM, because we are taking width 2 times, so it will be 2 GM. So you can also see previous lecture how we find out gain of this, and Vt function of VICM. Vt is output, so this will come like RT divided by 1 by 2 GM plus RT. Okay, let's find out gain and input output relationship. You see VICM. So first we will find out GM for this circuit, ISC by VICM. ISC is basically equals to ID. So this is ID by VICM, because if we apply KCL at this node, this output node, so ID is GM into VICM. Okay, so I did small mistake. Okay, so we need to find out this GM, which is ISC upon VICM. ISC equals to ID. From here we can apply KCL, and ID equals to GM. So for this device, this is same device, so GM is 2 GM. So we will write here 2 GM into VICM, because output is 0. So ISC upon VICM equals to 2 GM. So this is GM. And output resistance we need to find out. Output resistance is upper side 1 by 2 GM, lower side 1 by RT, and both are in parallel. So you can drive expression for that. So R out, you can write it like both are in parallel, 1 by 2 GM into RT, 1 by 2 GM plus RT. So